Welcome back. This is part 2. In part 1, we followed a single request from your browser through DNS, a secure connection, and HTTP, all the way to the server. Now, that server needs data. So, in this part, we cover where the data lives and how we make it fast databases, then indexing, caching, and CDNs. Let's start with the database itself. Okay, the server needs data, the product's price, how many are in stock, your past orders. Now, you might think just keep it in a file. But a file stops working the moment you have many users reading and writing at once. And huge amounts of data you need to search quickly. Under requirement that you never lose anything. So instead, we use a database, which is at high level a specialized program built to store data safely and give it back quickly, even with thousands of people using it at the same time. The most classic type is the relational database. This is your MySQL, your PostgreSQL, and the SQL databases. And the idea is simple and powerful. You store data in tables like a spreadsheet. So you have a users table, a products table, an orders table. Each table has rows, one per user, say, and columns like name and email. And here is the relational part. Tables can be linked. An order row can point to the user who placed it. So you can ask, give me all the orders for this user, and it connects them. And the language you use to ask these questions is SQL, structured query language. Now, the single most important thing about a relational database and a concept that underpins a lot of what follows is that it gives you ACID guarantees. ACID is four letters and each one is a promise. A is atomicity. A group of changes is all or nothing. Either every step happens or none does. C is consistency. The database never lets its own rules be broken, like stock going below zero. I is isolation. When many people are making changes at the same time, they do not corrupt each other. Each transaction behaves as if it were alone. And D is durability. Once the database says saved, it is truly saved, even if the power goes out 1 second later. And those last two have real missions behind them. For isolation, imagine two people buying the last item at the same instant. Without isolation, both read stock 1, both sell it, and you have sold something you do not have. So, the database makes one of them wait, usually by locking that row, until the first one finishes. And for durability, before the database says saved, it first writes a change into an append only log on disk. So, if the power goes off, it reads that log when it comes back and replays anything that was not fully written. And the tool that gives you all of this is a transaction, a bundle of changes that the database treats as one single all or nothing unit. Let's make it concrete. When you check out, three things must happen together inside your own database. Create the order row, reduce the stock by one, and write a payment attempt record. A transaction guarantees you can never end up with, say, the stock reduced but the order didn't get created. Either all three commit together or the whole thing rolls back as if nothing happened. And one important detail, notice that charging the card is not in that list. The actual charge goes to an outside company like Stripe over the network, and you cannot roll back an outside company. So you never put that call inside your transaction. You commit your rows first, then call the payment provider, and you send a unique idempotency key so that a retry never charges twice. Later, a reconciliation job compares your payment attempt rows against theirs and fixes anything that disagrees. That is why anything involving money almost always lives in a relational database. So, the relational database is where our store keeps its truth, the real products, the real orders, the real stock safely. But relational is not the only kind of database, and which kind you pick is the one of the most common interview questions there is. So, let's talk about SQL versus NoSQL. Okay, so we have the relational SQL database, but you will constantly hear about NoSQL databases as well. And SQL or NoSQL is one of the most asked interview questions. So let's be clear about it. And the honest answer is it's not a trade off, not one being newer or better. The SQL database, as we saw, gives you tables, relationships, and strong asset guarantees. It is brilliant when your data is structured and connected, and correctness really matters. Its cost is that it's stricter and traditionally harder to spread across many machines. NoSQL is really an umbrella for several kinds of databases that each relax some of these rules to get something else, usually more flexibility or more scale. And there are four families worth knowing. 1. Key value stores like Redis or DynamoDB. You store a value under a key and you look it up by that key. Extremely fast, great for caching sessions. 2. Document databases like MongoDB. You store flexible documents, basically JSON, which is just a simple readable way of writing structured data as text with no fixed columns. Good when your data shape changes a lot. 3. Wide column stores like Cassandra, built to handle massive amounts of writes across many machines. And 4. Graph databases like Neo4j, built for data that is all about relationships like a social network. And many NoSQL databases follow a model called BASE that stands for basically available, soft state, eventually consistent instead of acid. The key idea to remember is that last part, eventual consistency, meaning if you write something and then immediately read it from another copy, you might get a slightly old answer for a short moment until the copies catch up. That sounds bad, but for a lot of things like a like count, a view count, it is completely fine. And in return, you get huge scale. So the trade is SQL gives you strong consistency and relationships. NoSQL often trades a little of that away for scale and flexibility. So, how do you pick in an interview? Simple rule. Use a SQL database when your data is structured, has clear relationships, and needs strong correctness. Anything with money, orders, users. Use a NoSQL database when you need massive scale, or a flexible shape, or one specific extremely fast access pattern. And honestly, real systems use both. And two quick related pieces because a real store needs them. The product images do not go in the database at all. Big files go in object storage, like Amazon S3, which is a service built just for storing files cheaply. And search, when you type words in that search box, usually goes to a separate search engine like Elasticsearch, which is built to find and rank text. A normal database can do basic text search. Postgres and MySQL both have full text features, but a search engine is built for ranking, typo tolerance, and doing it at scale. It is worth being able to separate those two out rather than saying the database for everything. So, in our store, the orders and users sit in SQL database. The sessions might sit in a key value store. The images sit in object storage and search sits in a search engine. Now, even with the right database, one problem remains. As data grows, finding a single row can get slow. And the fix for that is a concept called indexing. That is next. Okay, so let's say our store's user table has 10 million users, right? And you want to log in. So the database needs to find the one row where the email matches yours. The naive way, check every single row one by one until it finds a match. With 10 million rows, that is painfully slow. And this is exactly the problem that indexing solves. Another very common interview topic. An index is a separate data structure that the database keeps on the side, which lets it jump straight to the row you want without scanning everything. The simplest way to picture it is exactly like the index at the back of a textbook. Instead of reading every page to find one topic, you look it up in the index and it tells you the exact page. A database index does the same thing for your rows. And how it works. At high level, the index keeps the values in a structure called a B tree. And a B tree is a short wide tree. The top node holds the few values that split the whole range into parts, let's say up to M and after M. And each part points down to a node one level below, which splits again. And the bottom level holds the actual values, each with a pointer to where that row physically sits on the disk. Now, here is why it is fast. Because every node holds hundreds of values, the tree stays very shallow. Even for 10 million rows, it is only 3 or 4 levels deep. So the database does 3 or 4 hops instead of 10 million checks. And each hop throws away most of the data that is left. And the tree rebalances itself as you insert new rows, which is how it stays shallow and the table grows. That is the whole magic. But, and this is the part people forget, an index is not free. Two costs. One, it takes extra storage since it is a whole separate structure. And two, and more importantly, it slows down writes because every time you add or change a row, the database has to update the index as well. So the rule is put an index on the columns you frequently search or sort by, like email or order date. But do not index everything, or your writes will become very slow. And you can also make a composite index on two columns together for queries that filter on both. So, in our store, indexing is what makes login by email or find by orders feel instant, even with millions of rows. But even a fast, well indexed database has limits. If millions of people hit it at once, it becomes a bottleneck. So, the next idea is about not asking the database so often, and that is caching. Okay, our database is fast, but it can still only handle so many requests per second. And the same popular product page might be requested a million times an hour. Asking the database to fetch the exact same data a million times is wasteful, and eventually it becomes a bottleneck. So the idea is keep a copy of the answer somewhere much faster and reuse it. And that copy is called a cache. This is one of the most important scaling tools there is. A cache at high level is a small, extremely fast store, usually kept in memory, using something like Redis or Memcached, that holds recently used data so you do not have to go all the way to the slower database. Memory is far faster than disk, so a cache hit can be, let's say, 100 times quicker than a database query. And the most common pattern is called cache aside, and it is worth knowing by name. It works like this. A request comes in for the product price. The server first checks the cache. If the data is there, we call that a cache hit. It returns it immediately and never touches the database. If it is not there, a cache miss. The server goes to the database, gets the data, stores a copy in the cache, and returns it. So the first person pays the slow price. Everyone after them gets the fast one. The whole point is to get as many hits as possible. There are other patterns as well. Write through, where you update the cache and database together, and write back, where you write to the cache first and the database later. But cache aside is the one to know first. Now, caching has two famous hard problems and they are worth knowing properly. The first is eviction. A cache is small, so when it fills up, it must throw something out. The most common rule is LRU, least recently used. Throw out whatever has not been touched in the longest time. And each entry can also have a TTL, a time to live, after which it expires automatically. And the second, harder problem is invalidation. The fact that a cache is a copy. So, when the real data changes in the database, your cached copy is now wrong. It is stale. Deciding when to update or delete cached copies is genuinely one of the hardest problems in this field. And there are two standard ways to handle it. One, whenever you write a row in the database, you also delete that key from the cache. So the next reader is forced to fetch the fresh value. And two, you simply accept a short TTL, let's say 60 seconds, and live with the data that is almost 60 seconds old. Most real systems use a mix of both. And there is one more called a cache stampede. If a popular cached item expires, suddenly thousands of requests all miss at once and hit the database together, which can overwhelm it. And the fix is quite simple. You let one request go and rebuild the value while the others wait for it. And you spread the expiry times slightly so 1,000 keys do not expire in the very same second. Worth naming. So, in our store, caching is what lets a hugely popular product page be served instantly to millions while barely touching the database. But there is one kind of slowness even a cache cannot fix, the physical distance between the user and the server. And the fix for that is our next concept, the CDN. Okay, so caching made our database faster, but here is a different kind of slowness. Our server might be in, let's say, America and a user in India. Now, no matter how fast our server is, the request has to physically travel across the planet and back. And that distance alone adds real delay because even at the speed of light through cables, it is a long way. And this matters most for the big files, images, videos, style sheets. So, how do we fix distance? We bring the content closer to the user, and that is CDN. CDN stands for Content Delivery Network. At high level, it is a large set of servers spread all over the world. These are called edge servers, and each one keeps a copy of your website's static content, the images, the CSS, the JavaScript, sometimes whole pages. So instead of every user fetching an image all the way from your one server, they fetch it from an edge server near them. Someone in India gets it from an edge in India. And how does your browser even know which edge is nearest? This is where DNS comes back from part 1. When you look up the address for that image, the CDN's own DNS servers look at where the request came from and answers with the address of an edge close to you. So, a user in India and a user in Germany ask for the exact same name and get back two different addresses. You do nothing, the answer itself is personalized. The distance and therefore the delay drops massively. And how does the content get to all those edge servers? The common way is called pull. The first time a user in a region requests an image, the nearby edge does not have it yet. A miss, so it fetches it once from your main server, which we call the origin, keeps a copy and serves it. Every user after that in that region gets the local copy, a hit, just like our cache, but spread across the globe. And it uses a TTL as well to decide how long to keep each copy before checking the origin again. One important distinction, a CDN is mainly for static content, the stuff that is the same for everyone. Images, videos, files, your personalized content, your cart, your account page is dynamic, different per user, so it usually cannot be cached at the edge and still goes to your server. So, in our store, the CDN is what makes product images and pages load quickly for users everywhere in the world. while also taking huge load off the main servers. And that closes part 2. We now have a server, a database, an index, a cache, and a CDN. One of everything running nicely. But what happens when one of everything is not enough? When the traffic is simply too much for a single mission? That whole question, scaling, is part 3. See you there.